Watch this generated 3D head model. It spins cleanly in isolation, representing the standard demo for new generative models, until it violently collapses under the weight of an actual production environment. A true production gauntlet requires a model to survive integration. It must execute a fixed script, sync perfectly to an audio track, maintain character continuity across multiple shots, and hand a clean alpha channel to a compositor downstream. To test this resilience, the Open Video Model Platform architecture imposes a severe hardware constraint. The entire end-to-end narrative workflow operates locally on a single consumer GPU, specifically an RTX 5080 laptop with exactly 16 gigabytes of VRAM. Running an entire 3D ecosystem in this space requires strict residency rules. The architecture standardizes a heavy engine code ceiling at 14.0 gigabytes, leaving exactly 2 gigabytes protected for the Windows display, WDDM overhead, and Comfy UI graph buffers. There are no cloud computing lanes to offload the rendering. The system executes entirely offline, issuing strict sequential VRAM leases. No two heavy models are ever permitted to reside in memory at the same time. Treating generative 3D models as standalone toys masks their instability and high resource demands. Determining their true viability requires forcing them through this continuous, resource-starved narrative harness to see if they can produce a finished episode without crashing. Chaining disparate generative AI libraries on a single machine guarantees severe dependency conflicts. Competing PyTorch versions and conflicting CUDA requirements will quickly corrupt the primary virtual environment and halt the pipeline. Models execute in isolated sidecars, communicating with the main environment exclusively via a JSON text bridge. Loading requires a strict VRAM lease capped at 14.0 gigabytes, protecting a 2 gigabyte margin. Upon completion, the sidecar terminates entirely, returning the VRAM footprint to absolute zero. Even lightweight helper models like depth estimators and retopology tools operate under this exact protocol. They receive no co-residency exceptions and must fully load, execute, and evict before the next engine boots. Without enforcing total process isolation and absolute process-level memory eviction, executing a sequential multi-model 3D pipeline on a 16-gigabyte GPU is impossible. To generate the raw character topology, the pipeline utilizes slot 1. Here, pure torch diffusion geometry models process the input identity hash and output the initial 3D mesh. Loading these heavy DITE geometry models pushes the system's VRAM lease to its 14.0 gigabyte limit. Once the raw mesh file drops onto the hard drive, the slot 1 engine is immediately evicted to clear the board. Raw generation models frequently produce catastrophic topological failures. The most common error is a mass of unusable, jagged geometry pooling around the neck and shoulders, known as marching cube soup. Because of this, the raw generated output cannot be used immediately. It must pass through slot 1.5, a mandatory, non-generative mesh sanitization step required to cut away the unusable geometry. In this diagram, a bounding box encapsulates the jagged head geometry. To isolate the usable data, a horizontal plane intersects exactly at the midpoint. This decapitation slice aggressively discards all non-essential geometry below the neck. The remaining geometry undergoes headless sanitation protocols. The pipeline normalizes the mesh scale, removes loose floating parts, recalculates inverted normals, and algorithmically fills any structural holes. The architecture strictly bans generative mesh refiners for this cleanup phase. Autoregressive mesh models tend to hallucinate completely new geometry and will strip existing UV coordinate data from the file. In a narrative pipeline that demands precise facial deformation, these raw, unoptimized meshes remain functionally undrivable until subjected to this rigid, deterministic cleanup sequence. Compatible mesh topology alone is mathematically undrivable. Without embedded shape keys defining how the vertices should move, the animation drivers have no coordinate system to manipulate. To impose an external control structure, the pipeline uses a template-first shrink-wrap methodology. The jagged mesh surrounds a smooth canonical template and projects its vertices inward, shrink-wrapping tightly to match the underlying bones, baking exactly 52 ARKit shape key deltas into the geometry. If the wrapped mesh fails this 52-key conformance test, the system triggers an immediate fallback protocol.
The pipeline rejects the model and reroutes the generation to a low-poly, guaranteed manifold fallback mesh to prevent the render from corrupting.
This rigid transfer provides the system a universal control map. It ensures that regardless of which generative model produced the head, the final asset is controlled by a consistent set of 52 universal parameters.
The animation sequence answers to a single authority, the master audio file. The audio track is frozen, read-only, and byte-identical. It never bends to accommodate the model. The model serves the audio's timing. The audio strictly dictates the total frame count of the visual sequence. The compositor calculates the total video frames by multiplying the exact length of the audio seconds by the target frame rate, holding the last frame for any subframe remainders. The animation process, known as Slot 2, splits into two distinct operational phases. Phase 2A extracts the performance curves, and Phase 2B deforms the actual mesh. During Phase 2A, the model algorithmically evaluates the frequency and amplitude of the audio file. From this sound envelope, it extracts exactly 52 specific ARKit weight curves for every single frame. The pipeline heavily favors fully deterministic drivers for this extraction. Deterministic models eliminate lip-sync drift and procedural variance, ensuring the calculated weights map cleanly to the phonetic timing. Once the curves are generated, Phase 2B executes. The computational engine takes the newly calculated array of 52 curve weights and feeds them directly into the 52 shape keys of the wrapped GLB file, driving the physical facial animation. Because Phase 2A operates independently of the mesh geometry, the pipeline can cache these 52 weight curves against a cryptographic hash of the source audio segment. This eliminates the need to recalculate the performance data for repeated renders. Within this architecture, the visual model possesses zero temporal agency. The face exists exclusively to execute the exact mathematical dictates derived from the master audio file. Even with the mesh perfectly synchronized, generating the final visual composite introduces a fatal vulnerability. Attempting to render complex 3D scenes on a highly constrained consumer GPU often causes the final phase to crash. Custom CUDA rasterization nodes operating at the 16 GB limit cause severe VRAM fragmentation. This fragmentation leads to silent out-of-memory errors that instantly kill the render right before completion. The architectural bypass offloads final composition to a standalone, headless subprocess. The output branches into a multi-pass EXR tree with parallel channels for normals, depth, and shadow. This isolated process requires under 3 GB, safely avoiding the 14 GB code ceiling. This method allows the compositor to extract multiple structural layers from a single geometric load. From one file, the system outputs procedural eye gaze adjustments, accurate contact shadows, and ambient occlusion, all layered perfectly. Completely decoupling the final rendering engine from the heavy PyTorch memory stack prevents late-stage pipeline collapse and guarantees a clean, uncorrupted handoff to the compositor. Because every stage of the pipeline, from mesh generation to curve extraction, is keyed to unique content hashes and the same frozen audio track, the system can reconstruct the exact same scene with byte-identical results across multiple runs. Look at this interface. A scrolling vertical MIDI piano roll is directly driving the rapid twitching deformations of an abstract wireframe face. The pipeline takes the 52 isolated facial curves generated by the audio and serializes them into this universal exportable MIDI protocol. Exporting this performance data allows engineers to cross-wire the architectural elements. The precise phonetic amplitudes driving the character's jaw can simultaneously control environmental lighting strobes or trigger a procedural camera shake right on the syllable. The rendering artifacts themselves become a visual tool. By removing photoreal textures and utilizing raw normal map passes, the geometry reveals the physical topography of the expression, rendering structural movement rather than simulated skin. When sudden memory spikes overwhelm the GPU, the hard constraints force a graceful failure, collapsing the high-fidelity output into a highly visible, low-polygon safety state, while maintaining perfect lip-sync with the audio. Underneath the geometry, ledger hashes mathematically lock the character identity to its raw underlying topology. A continuity change in the hash indicates a deviation in the structure itself, independent of any surface-level visual traits applied later. The absolute temporal supremacy of the frozen audio dictates every visual action.
the image must synchronize to a predetermined timeline, creating a visual logic bound entirely by inevitable predefined pacing. By prioritizing hardware survival through strict leases and frozen audio tracks, the pipeline creates a production environment where the visual style is a direct, measurable reflection of the machine's own technical limits.